Okay, in the last lecture we talked about enolates and preparing enolates, and what I want to do is go back and talk a little bit about enols and their stability, and then move back into enolates and start some of the reactions of enolates that, again, we're in chapter 26, which is broadly enolate and condensation chemistry. So in terms of enols themselves, remember that an enol is basically an alkene and an alcohol where the OH group is directly attached to the double bond. And with that enol, if I move this hydrogen over here, remember that we first saw these in the context of taking a triple bond and adding to it H plus and H2O. So we did Markovnikov addition, which ended up adding an H to the carbon with the most hydrogens, and ultimately an OH group to the other carbon, reducing the triple bond down to a double bond. We then said that enols, for the most part, are unstable, which is true. We'll get into a couple of examples of enols that are stable. But for the most part, enols are unstable, and they undergo a tautomerization equilibrium where we can take the electrons and move them like this, where the hydrogen of the OH ends up being transferred from the O atom down to the carbon, so that we end up making the carbonyl, and then that H ends up on, in this case, what would be a CH3, and then there'd be another CH3 over here. So for your average run-of-the-mill enol, the equilibrium lies far more towards the ketone. So in general, that equilibrium lies to the right. Now, there are some enols that are actually fairly stable, and I'm going to talk about those. And those are the enols that are formed from what are called beta diketones. Those of you that go on and take physical chemistry lab, you'll be doing, well, hopefully you'll be doing it either way, whether it's in the lab or whether it's online, who knows at this point. You will be doing an experiment with beta diketones. That much I can guarantee you. So let's take a look at a simple beta diketone, including what does it mean to be a beta diketone. Well, if we start off with the carbonyl, remember the alpha carbon is the one attached to the carbonyl, and then we go down the line beta and gamma and delta and all of those. So this would be called a beta dicarbonyl, which is basically using the Greek terminology for a 1,3. In this case, a 1,3 diketone. And in this specific case, this is a molecule called acetyl acetone, which is abbreviated ACAC. And it actually can form an enol in an equilibrium, and I'm going to have to move that alpha sign. So if I take one of these, this hydrogen, and I actually was to move this pair of electrons like so, move this pair of electrons out, and take that hydrogen and transfer it up to the oxygen, what I would end up with is an OH group with a double bond. So there's my enol part, and here is my beta ketone part. Now, the equilibrium for this lies far, far to the right. As a matter of fact, if you have this ACAC, as you'll see if you go on and take physical chemistry lab, that it is predominantly, even straight from the bottle, it is in this enol form. Why? Because that hydrogen can form an intramolecular hydrogen bond, intra meaning within the molecule, to the carbonyl, and it forms a very stable 6-membered ring with the intramolecular hydrogen bond. So the thermodynamics of this are that the enol is the predominant form, even straight from the bottle. And in PChem lab, you'll determine this equilibrium constant, which is called K enol. You'll determine that, and you'll determine it as a function of temperature to get more ideas about the thermodynamics of this process. So beta diketones are one of the few molecules where you can actually have the enol be far more stable than the ketone itself. Run-of-the-mill enols, like this is acetone, right, from lab. The enol of acetone is very unstable. And so I think it's only been in the last probably 20 to 30 years that anybody was able to isolate the enol of acetone because it is so unstable. I seem to recall when I was a postdoc doing X-ray crystallography at Brown that somebody who actually has written a organic text, my recollection is it was Mark Loudon, and he had sent us a crystal asking us to determine whether or not it was actually the enol of acetone, and if I remember correctly, we could never quite get a good enough crystal to do that analysis. But I think since then, people have published that indeed the enol of acetone, again, there's a CH3 group here, not enol group, that it's very, very unstable and very difficult to isolate. But people have isolated in the last 20 to 30 years. So for beta diketones, it's very common to have the enol as the more stable form. Now that kind of breaks down when we start looking at the enols of carboxylic acid derivatives. So for a carboxylic acid derivative, such as an ester, let's say, that the equilibrium here lies predominantly towards the ester. Only a very, very small amount of enol from the ester, only a very, very tiny amount is actually in the enol form for an ester or for any carboxylic acid derivative. As a matter of fact, the other molecule that the students do in PChem lab is to look at the ACAC molecule that I just gave you, but also then they look at this molecule, which is called ethyl ACAC. It has a different name. It's acetoacetate as opposed to acetone. But in this case, the equilibrium between forming its enol and forming the ketone, the equilibrium lies predominantly towards the diketone form. So even though it can form a hydrogen bond, it doesn't in solution. It's very few percent are in the enol form, even with the help of forming an intramolecular hydrogen bond. So that's a little bit more about the stability of enols. And again, to summarize, for the most part, simple enols really are too unstable, like the enol of acetone. On the other hand, beta diketones are very good at forming enols, and they will actually predominate in their enol form because the formation of the hydrogen bond and also the formation of a 6-membered ring with the double bond. And then also, well, let me just go back here for a moment. There's one other factor that I did not include in this. Okay, there is this intermolecular hydrogen bond that is stabilizing, so that's the first factor why the enol is stable. The second factor is that that double bond is in conjugation with the carbonyl double bond. And so those two factors are what cause the enol to become very stable and to be the predominant form for beta diketones. Unfortunately, for carboxylic acid derivatives, they only form a very small amount, like esters. They form a very, very small amount of enol, and even beta, this would be called a beta keto ester, where the ketone group is at the beta position relative to the ester. That molecule there's only a very small amount of this formed, and so for any carboxylic acid derivative, you don't get very much enol at all. And in PChem lab, you would study that equilibrium and find out that it's completely different. So now let's talk a little bit about forming enolates using bases, and I want to throw in a kinetic versus thermodynamic that's discussed in the Top Hat book. So let's take that ketone, and we'll make it unsymmetrical so that it has two different beta hydrogens that can be removed two different alpha hydrogens that can be removed by a base. So in this case, if we remove alpha hydrogen, I'm just so used to saying beta hydrogen with our E2 eliminations, if we were to remove alpha hydrogen A, so in other words, if we had a base come in and grab the beta or alpha hydrogen A, we'll end up with a negative charge there. And if our base is to come in and remove, let's say, alpha hydrogen B, then we would have the negative charge there. Now, you may say, well, okay, what about kinetic and thermodynamic? Which one of those two anions is the most stable? And what I would say is, let's draw the resonance structure. So let's take this pair of electrons, move it here to form the resonance structure for that enolate ion, which would have the O- up here and the double bond there, versus moving this pair of electrons and forming the resonance structure with the double bond in that position. So which of those two molecules would you say, which of those two enolates would you say is the more stable one? If it was me, I would say that this is more stable because it's got a double bond that is more substituted. This product is going to be the less stable product. So if I want to form the more stable product, that would be what we would call the thermodynamic product, right? From 1,2,1,4 addition. Well, what kinds of conditions would give me the thermodynamic or more stable product? Number one, I need to use a base that can get at each one of those alpha hydrogens equally well. So don't use a sterically hindered base. And secondly, for thermodynamics, I'm going to want to use a higher temperature. So typically what we find is that if we use a base, something like methoxide, at maybe room temperature, we would favor the formation of the thermodynamic product. So we're taking into account all the factors we talked about before with 1,2 and 1,4 addition by simply saying, okay, we're going to use a small base so it can deprotonate either hydrogen, and let's use a high temperature as opposed to a low temperature where we're under thermodynamic conditions and not a kinetic product that is the one that's formed first. So this would be our thermodynamic product, and I would use a small base at room temperature. Now, if I wanted to form the other product, what should I use? Well, if I want to form the other product, what I need to do is I need to use a sterically hindered base, and I should use that sterically hindered base at a low temperature. And low temperatures for these reactions is minus 78 degrees Celsius. And you might say, well, how convenient is it to do a reaction at minus 78? Minus 78 degrees is actually, you can make that very easily by using dry ice, which is solid carbon dioxide, along with something like isopropanol, which is just simply rubbing alcohol. So if you mix dry ice and isopropanol together, you easily get a minus 78 degree slush is what we call it. And so then you just stick your round bottom in there, and voila, you can do a reaction at minus 78 degrees. So the idea here is that I'm forcing the base to react only with alpha hydrogen B. So the sterically hindered base is going to be will not be able to remove that sterically hindered hydrogen. Instead, the sterically hindered base will have no choice but to remove the less hindered beta or alpha hydrogen A. And so in that case, I'm going to form this enolate, which is the less stable, but comes from the more sterically accessible hydrogen. So again, I'm taking and using the factors that we talked about for kinetic and thermodynamic products, and I'm simply applying it to the reactions of, in this case, the formations of enolates when I can form more than one type of enolate. Now, you might say, what's your sterically hindered strong base going to look like? Tertiary butoxide? Yeah, I would use our new friend, I don't know, I haven't done a whole lot with this, but certainly been in that area for a long, long time. We would use our sterically hindered strong base called LDA, lithium diisopropylamide. Personally, again, from the last lecture, the amide base that has paid my bills for many years was this one, which has the same basic features, sterically hindered and a strong nitrogen base. So these are the kinds of, this is the kind of thermodynamic versus kinetic reactions that we can do in the formation of enolates. We're not really going to do that because, as you're going to find out, we're going to do most of our reactions with symmetrical enolates just to avoid the complication that happens when the reaction is unsymmetrical. Okay, so let's talk a little bit about, and I'm going through the beginning of the chapter here to kind of mop up some of the topics that I had given you before, and that is basically what is called a Broma Form or an Iodoform reaction. And this was used back in the day, like when I was an undergrad. We used this reaction to try and figure out if we knew we had a ketone, whether or not it was a methyl ketone. And so what we would do is we would take a ketone that was a methyl ketone, so it had to have a CH3 group over here, and we would react it with iodine and hydroxide. And in this case, what would happen is that if we had the methyl group side with iodine, and here's what's going to happen. If we look at our methyl group here, our hydroxide is going to come in and deprotonate that to form the enolate, and I'm going to keep the negative charge on the carbon. Then what's going to happen is that enolate would end up reacting with iodine as a nucleophile, so it would react with one of the iodines and kick off the other one, so that we would end up basically adding an iodine to the methyl carbon. Now, once you add an electron withdrawing group like iodine or bromine or chlorine, and this is done primarily with iodine, it will basically remove electron density from this carbon, so that the next equivalent of hydroxide that wants to come in and deprotonate that alpha hydrogen, that enolate will be stabilized, because that carbon is going to have some of its negative charge pulled away from it by the electronegative iodine. So then it will react with another iodine molecule, where the C- will react with the I2, and we will end up then adding a second iodine. And then there's nothing. Now we've got two iodines on there, which is going to pull electron density twice as much. And so a third equivalent of hydroxide will come in, react with that alpha hydrogen, and we will end up now with a negative charge and two iodines. Those two iodines are able to stabilize the C-, so that it will now react with a third iodine molecule. And in reacting with the third iodine molecule, we end up completely replacing all of the alpha hydrogens on the methyl group with iodines. But we are not done yet. The next hydroxide is going to be able to come in and attack that carbon and have the pair of electrons move up to the oxygen. So that I'm going to make my O- now with my hydroxide in place, and my carbon with 3 iodines on it. And part of the reason why the hydroxide can go ahead and attack that carbonyl is because the iodines are pulling electron density out of this carbon, making it severely delta positive, which is then going to pull electron density from the carbonyl. It's going to make it more delta positive and therefore more electrophilic. Now, once I add the hydroxide to the carbonyl, I get an O-. How many times have we said this semester that O- is going to want to bring its pair of electrons down, but it needs a good leaving group? Well, guess what? The 3 iodines attached to the carbon are going to make it a good leaving group. So not the hydroxide will leave, but the Ci3 will leave. And so I will end up over here with the carbonyl, the carboxylic acid, and now I'm going to end up with 3 iodines on my C-. Again, the C- is stable because the 3 iodines are each pulling electron density out of the carbon, so it's basically delocalizing that negative charge. C- is still a fairly strong base, so it's going to go ahead and deprotonate the carboxylic acid. And what we will end up forming then, on the next slide, is we'll end up forming a carboxylate and HCl3. So we're going to end up forming the carboxylate salt, or the carboxylate, and then Ci3H. So this reaction, this is actually called the Iodoform reaction. There's also a Broma Form and probably chloroform, but let's talk a little bit about that. So what is chloroform? Chloroform is Cl3 with an H on it. That is chloroform. This is called iodoform. And the visual test that we used to have to do if we were determining the structure of an unknown prior to a lot of spectroscopy is if we thought we had a methyl ketone, what we would do is we would add to that methyl ketone a mixture of iodine and base. And it would go through that reaction and form iodoform. Now, iodoform is it's kind of a light yellow precipitate, so that if we did that reaction and all of a sudden we saw this yellow precipitate come precipitating out of solution, we would know that we had a methyl ketone because we know that we formed the iodoform. And then when I was an undergraduate, and I don't remember having to do this explicitly, but if that happened, you had to recrystallize the iodoform and take a melting point of it to confirm the fact that it was indeed iodoform. So it provided a very easy visual test that you indeed had a methyl ketone as opposed to an ethyl, or I guess anything other than a methyl ketone. Now notice also in terms of the transformation here that I am taking a methyl ketone, and by using iodine and hydroxide, I basically have now oxidized that ketone to, in essence, a carboxylic acid. So you could think of it that way in terms of a transformation to form a carboxylic acid out of a methyl ketone, but it's very specific just for methyl ketones. Okay, so that's the iodoform, and the textbook used bromine as its example for what is called the haloform or the Broma Form reaction. But it's primarily done with iodoform or with iodine so that you can get that nice yellow precipitate to come out, and you can say, yes, I know I have a ketone, and now I know I have a methyl ketone. Again, in the days before spectroscopy, that was very, very, very helpful. Okay, let's talk about, before we get into enolate chemistry, one more reaction that isn't really related to enolate chemistry, which is called the Hell-Volhard-Solinsky reaction. And in the Hell-Volhard-Solinsky reaction, or what is called HVZ reaction, what I'm going to do is I'm going to take my ketone or carboxylic acid, I'm going to treat it with bromine and PBr3, which is the equivalent of PCl3, and I'm going to end up then putting a bromine onto the carboxylic acid. Now you might say, well, wait, in the last lecture video, you said that all we had to do was simply deprotonate the alpha hydrogen and then react it with bromine. Yeah, that's for ketones and aldehydes. But that doesn't work with a carboxylic acid, because remember that if I treat a carboxylic acid with any kind of base, what's going to happen? I'm going to remove the carboxylic acid proton. And once I would do that, I would form then the carboxylate group here. Well, that carboxylate is going to have a negative charge. I can't put another negative charge on this carbon by deprotonating it, because then I'm going to have two negative charges like next to each other, and that just isn't going to work. So I need an alternative way to brominate, to alpha brominate carboxylic acids. And so this is the method that we do it, and this was a method developed by Hell, Volhard, and Solinsky. And so this mechanism gets a little weird, but the first step is, let's take our carboxylic acid and let's react it with PBr3. Now, PBr3 is an equivalent of PCl3, which is like SOCl2. So what's the first reaction that I'm going to do? I'm going to convert the carboxylic acid into the carboxylic acid, now bromide. Once I have the carboxylic acid bromide, we can then think about forming the enolate of that. So I would take this hydrogen, I would move this pair of electrons here, move that pair of electrons there, and this is an equilibrium, not a resonance structure. But then what I would do is I would go ahead and form that enol. Once I form that enol, I'm now going to go ahead and add my bromine, my Br2, so this pair of electrons is going to come down here. This pair of electrons involved in the double bond is going to react with the bromine and kick off the Br-. So I didn't do anything with base here, because again, base would have deprotonated the carboxylic acid. So if I do that, then what I'm going to end up with is now a bromine attached to what is still the alpha carbon. So then things get to be kind of weird, because you might say, well, once you make that compound, wouldn't it be okay to just react it with water and convert it back to the carboxylic acid? But that's actually not what happens in this particular case. So when we're doing this reaction, what we're going to do is we're going to use excess carboxylic acid in this case. And so what's going to happen in the next step is that this alpha brominated species is going to react with an unreacted or an unconverted carboxylic acid. So if I go to the next steps, then what's going to happen is, because of the bromine pulling electron density out of that carbon, and also because basically this carbon over here is going to pull some electron density out of the carbonyl, that's going to make the carbonyl very delta positive. So that now what's going to happen is, and this is the proposed mechanism, is that now I'm going to take my oxygen of my carboxylic acid, and remember that for the ester or the carboxylic acid, this carbon has a slightly positive charge on it, and the oxygen has a slightly negative charge. So it's the nucleophile, and it's going to attack the carbonyl. So when it does that, I'm going to form my O-. My carbonyl group is going to have added to my carbonyl oxygen, will have added to this carbon, and there would be a plus charge on that oxygen. Now that's not a great resonance, that's not a great structure, so let's go ahead and draw the resonance structure for this. And the resonance structure for this would be to say, you know what, I'm going to take a pair of electrons from the OH and I'm going to give my pair of electrons to the oxygen. So the resonance structure that would help, or probably be the more stable resonance structure, would be this. I would still have my O- up here, and then I would have the O there, and then I would have a C double bond O with an H, so that's going to have a positive charge, and then my RCH2 group over here. So all I'm doing is just writing a resonance structure that where the positive charge is now moved to basically a carbonyl. All right, that's great. So what happens next? And what happens next will be the following. that. Okay, so I'm going to bring this pair of electrons back down. I'm going to do it on this resonance structure, and when I do that, the bromine's going to leave. And so then what I'm going to end up with is reforming the carbonyl that is going to be attached to an oxygen that has a double bond and a positive charge on it, to the carbon with the OH up here, and then down here the R group as well. So now what's going to happen is that bromine that I just lost is going to come in. It's going to attack this carbon, and then this pair of electrons will go to the oxygen to complete its, to basically give it a neutral charge. So when that happens, I'm going to end up with that species. Now that's an interesting species that I'm going to have to rewrite and put it into a molecule that we're going to see in the future. So what I'm going to do is I'm going to put this molecule into, it's going to have an R with a CH with the BR there. Then it's going to have the C double bond O with the O here. And then on the other side, I'm going to have my C with my O, and I'm going to draw it deliberately this way with my BR and my CH2R group. Now, why did I write it that way? Because in essence, I'm going to have to cleave this molecule. And so the way I'm going to cleave this is by putting this into a six-membered ring where this hydrogen is going to be hydrogen bonded to that carbonyl. It's going to set it up to occur, the arrows to move in the following direction. And so here's how this is going to move I'm going to move the electrons in the following direction. So I'm going to bring this pair of electrons down. I am going to then break this carbon-oxygen bond and move that pair of electrons there. And then I'm going to use this pair of electrons from the carbonyl to bond that hydrogen. So in this six-membered ring with the hydrogen bond, or the six-membered transition state, what I'm going to end up doing is cleaving this bond. And so what am I going to end up with? Trying to write this in exactly the same format. So or same orientation, I'm going to end up with the OH there and the double bond there. On the other side, I'm going to end up with the carbon with the carbonyl, a CH2R group on one side, and the acid bromide on the other. So I'm going to end up then forming the carboxylic acid that's been brominated, and I'm going to end up then with the acid bromide on the other side. So this is a very complicated mechanism for Helmholtz-Solinsky, but again, the most important part here is that Helmholtz-Solinsky gives me a method to alpha brominate a carboxylic acid, which cannot be done like an enolate. That just, it will not react that way with an enolate molecule. Okay, so now let's jump into enolate chemistry and all of the various variations, I guess, on this. And so let's go back and talk about the idea of taking. We'll do this with an aldehyde first because it's easiest to see. So I'm going to take this aldehyde and I'm going to treat this with a mixture of alcohol and hydroxide. Okay, so remember, the mixture of the alcohol and the hydroxide from last time produces some alkoxide, and that alkoxide is going to go ahead and it's going to deprotonate the alpha hydrogen of the aldehyde in this case to form an enolate. And we're going to keep the negative charge on the carbon because that's what we're going to react. Now I'm simplifying this because I'm using an aldehyde so that we don't have to worry about if there's an alpha hydrogen over on the other side. There's not. So we're going to focus just on one side. I have now made the enolate. Now, this all of this turns out to be an equilibrium reaction. So that while the alkoxide deprotonates some aldehyde to form an enolate, there is unenolized aldehyde left in the solution. And so now what I'm going to do is now I'm going to take this C- and I'm going to do what C- do with carbonyls. Right? When we took a CH3- and we with a magnesium Br+, or with a lithium, what happened? It would come over and it would attack the carbonyl. Well, this is going to do the same thing. The C- is going to come over and attack the carbonyl exactly like a Grignard would. Now, I need numbers to keep track of this. So here's what I'm going to do. I'm going to call the unenolized carbonyl carbon 1, carbon 2, carbon 3. And then over here I'm going to have carbon 4, carbon 5, and carbon 6. So when that reaction occurs, I'm going to end up, and I'm going to rewrite my unenolized ketone is going to look like this. Right? So carbon 1, carbon 2, carbon 3. And the CH group, which was carbon 5, reacted with that carbonyl, carbonyl 1. And then down here I'm going to have what? I'm going to have a CH3 attached, and on the other side I'm going to have an aldehyde attached. So I will end up making that alkoxide, and that alkoxide will pick up a proton from the solvent, so that initially what I will make looks like this. And I'm going to rewrite it in its form that I just did, but then I'm going to go ahead and I'm going to write it sort of all in one line. Okay, so this was carbon 1, this was carbon 2, this was carbon 3, this was carbon 5, this was carbon 4, and this was carbon 6. Okay, now what did I just make? Well, starting with the carbonyl, this is the alpha carbon, this is the beta carbon. So this is called a beta hydroxy aldehyde in this case. And beta hydroxyaldehydes aren't too terribly bad. You can form them. You're going to have sometimes a hard time isolating them, but that can be done. So what I'd like to do is to write this beta hydroxyaldehyde in a straight line. So let's start with carbon 4 and write the aldehyde, then the CH group. That CH group is going to have a CH3. So here's carbon 4, 5, and 6. And what's carbon 5 attached to? It's attached to carbon 1, and then 2 and 3. So carbon 1 was originally the carbonyl. And what I'm going to do is I'm going to take carbon 5's hydrogen and I'm going to explicitly write it. So that's the same structure in a sort of linear fashion. Now, when you do these kinds of reactions, typically if you do these at either room temperature or with a little bit of heat, this molecule can actually undergo a dehydration reaction. And so what will happen is that I can lose the H and the OH. So I end up losing water in order to then form a double bond between carbons 5 and 1. So 4, 5, 6, 1, 2, and 3. Carbon 5 is now the alpha carbon, and carbon 1 here is now the beta carbon, and then 2 would be gamma and delta. What I just made was, I just made what is called an alpha beta unsaturated, unsaturated meaning double bond aldehyde in this case. So typically what we make when we do this type of reaction, this is what is called a self-Aldol condensation. Okay, self. It means that the enolized aldehyde reacts with the unenolized aldehyde, so in essence it's reacting with itself. Aldol. This product right here, which isn't very stable, which usually then is converted to the double bond, this is half alcohol, half aldehyde, and so it's called the aldol product. Condensation, whenever a reaction eliminates water, it's called a condensation reaction. So overall, if you react an aldehyde, and we'll talk about ketones in a minute, if you react an aldehyde with a combination hydroxide and alcohol, you'll end up doing a self-aldol condensation to first of all form the beta hydroxyaldehyde, which will then easily eliminate water to form the alpha beta unsaturated aldehyde. And so that is overall what is called a self-aldol condensation reaction. Okay, so I didn't really do anything new here except until I got to the dehydration part. And this is what I did part of my, or tried to do part of my doctoral thesis on aldol condensation reactions, and we tried to isolate one of these beta hydroxy, and they were a nightmare because they always wanted to dehydrate to form the alpha beta unsaturated molecule. Now why? Why would they want to dehydrate? Because then this double bond is in conjugation with the carbonyl double bond, and so that makes the molecule really stable. So it's very difficult to keep these things from dehydrating, although it can be done, but that's beyond the scope of what we want to talk about now. Okay, so that's a self-aldol condensation, and whether it's an aldehyde or a ketone, you get the same self-aldol reaction. Aldol doesn't always mean aldehyde, it can be ketone as well. So for instance, usually we like to do reactions with symmetrical ketones, so that way if I react this now with a combination of base and alcohol, I'm going to form an RO minus. That RO minus is going to come in, and in this case it doesn't matter which alpha hydrogen I react, it's going to deprotonate it, so I'm going to end up forming this enolate. That enolate then is going to react with some ketone that hasn't enolized. So it's going to react with this carbonyl, and the pair of electrons will go up here. This is where, again, it's really helpful sometimes to start numbering things. So maybe 1, 2, 3, 4, 5, and then over here 1, 2, 3, 4, and 5, or actually it'd probably be better that there's going to be too many 3s and 4s and 5s, so let's go ahead and just make it 6, 7, 8, 9, and 10. So that C minus is going to react with the carbonyl, which is 8. What I like to do, you can write the molecules either way. I'll write it differently than I just did. So in other words, I'm going to have the CH now. That CH will react with the carbonyl to make the O minus. That carbonyl has an ethyl group on one side and an ethyl group on the other. So again, carbon 1, 2, 3, 4, and 5, and then carbons 6, 7, 8, 9, and 10. And then that O minus will pick up a proton. It will deprotonate either the alcohol or water, because hydroxide comes in water. So it'll go ahead and deprotonate that. So I will make the product with the C double bond O, now with the CH, now attached to that OH, along with the CH3, CH2 on this side, and the CH2, CH3 on that side. Now again, taking this alpha, now in beta carbons, I now made the beta hydroxy ketone, and now I'm going to end up dehydrating my molecule so that I'm going to end up losing H2O, and I'm now going to end up forming the double bond between, again, 1, 2, 3, 4, and 5, 6, 7, 8, 9, and 10. So I'm going to end up forming the double bond between carbons 4 and 8. So let me write on the other side, carbon 8. Carbon 4 is attached to a methyl group, so that methyl group will go down here. My double bond will go there. And then carbon 8 here is attached to 2 ethyl groups. So there is my alpha and beta unsaturated ketone. So that's an aldol condensation with a self-aldol condensation with a ketone. And again, aldol can be used for either ketones or aldehydes. It doesn't have to. It doesn't have to be one, or it doesn't specifically refer to aldehydes. Okay, so that's a self-aldol condensation reaction. And what I will point out here is that this is a mess. The reason that aldol chemistry wasn't quite up to speed in the pre-1960s was that, just imagine I had an unsymmetrical ketone. Or even worse yet, imagine that I was trying to react that unsymmetrical ketone with this aldehyde. And I said, well, let's just go ahead and mix this with a combination of alcohol and hydroxide. How many different products could I get from this reaction? Well, I've got 2 possible enolates, 2 possible enolates on this ketone, 1 possible enolate formed on that aldehyde. So I've got the possibility of forming, in the self-aldol condensation reaction of the ketone, I could end up with 2 different alpha-beta unsaturated products, depending on how which enolate I formed, and having it do a self-aldol condensation on itself. So that would give me 2 different alpha-beta unsaturated ketones just in the self-condensation. Over here, I would get 1 product in the self-aldol condensation, because I can only form 1 enolate. And then if I did what's called a mixed aldol, where now the enolate of one reacts with the ketone of the other. So if I have the aldehyde, so if I had the enol of the aldehyde reacting with the ketone, that would be product number 4. And then I've got 2 different enolates. That should be enolate. The enolate of ketone, enolate 1, and enolate 2 of the ketone, reacting now with the aldehyde. That's products 5 and 6. There would be no preference over the formation of any one of those products as the major product. So what hampered aldol condensation chemistry prior to the development of bases like LDA was that you got this mixture of enolates, and then the mixture of them reacting with themselves and also then reacting with the other molecule, so that you would get 6 different products. Well, that's not productive. So what people would sometimes do is this. They always used a symmetrical aldehyde or ketone. Now you say symmetrical aldehyde, there is no such thing. Correct. Because if you have the aldehyde, you only have 1 alpha hydrogen that can be removed. But if you use a symmetrical ketone and you were to react it with something like benzaldehyde, where there are no alpha hydrogens, then you only make one. You would only make one enolate, and so that one enolate is going to react with the aldehyde simply because this aldehyde of benzaldehyde, there's no alpha hydrogen, so it can't form the enolate. So these were the kind of quote unquote mixed aldol reactions that were productive, but again, that's pretty limited. A symmetrical ketone or an aldehyde with an aldehyde, or ketone with no beta hydrogens, that limits the synthetic choices that you have. And again, that's why enolate and aldol chemistry did not come into play. It didn't become important until the 60s, or actually even later, with the development of these strong bases where I could form one enolate and react it with a ketone. So that's aldol condensation, both for a ketone and an aldehyde. And so what we will finish up the year with, yay, in the next lecture will be the final lecture video of the year, will be to talk about making different types of enolates and all the various combinations of reactions that we can do to form different types of molecules, but they're all going to be the same tedious set of mechanisms. Okay, so that's what we will end with in the next lecture video.